Welcome to the live space launch reboot of CUAVA-1. CUAVA-1 is the first satellite developed by the ARC Training Centre for CubeSats, UAVs and their applications. In a few moments, we'll have a Q&A session with Director Professor Eva Cairns and the CUAVA-1 engineering and payload teams, while we wait for countdown to launch. Before we begin, CUAVA would like to respectfully acknowledge the traditional owners of the land on which we stand today, the Gadigal and Wangal people of the Eora Nation, and pay respect to the traditional owners of all the lands on which CUAVA research is undertaken.
Welcome everybody. This is the reboot of our launch, and hopefully everything is going to go to plan tonight. We're ready for a short Q&A period, and then we hopefully will go to the launch itself. So please use the Q&A options here so as to be able to ask us questions or comments. But it's very good to see over 50 people here, including Anna. Anna from the ACMA, welcome. Great to have you with us. And it's a real pleasure to be here. So at the moment, I don't see any particular comments from anybody. Maybe I will just share a screen for a moment. And okay, so we'll answer Anita's question first. So I think you're probably commenting on the NASA screen, which is to my upper left. That's the live view of the rocket. It's a Falcon 9 Block 5 rocket, which carries a Dragon capsule, take us to the International Space Station. We'll reach there tomorrow. Those of you who are aficionados will know that it's launching from Launch Complex 39A, which is famous for carrying or being the place where almost all of the Apollos launched from to the moon, as well as approximately 50 shuttle flights. And then more recently, it's been leased by SpaceX and has been used for many of their launches. So it's quite a famous launch pad with lots of history. I suspect, though, Anita was commenting about the backdrop to Shirley-Ann Bai, who's the training center engineer. And behind Shirley-Ann, you can see the spacecraft before it's had its panels put on, or at least mostly. It's mostly during a stage where things have been integrated together. You can see different, let me try and annotate. So in the backdrop of Shirley-Ann Bai, you can see different panels there going transverse to the main axis. Those are the PCBs or electronics boards that contain, for instance, our payloads. And I thought I might just quickly show the screen to show a example of, well, a picture of CUAVA-1 itself. I think people can see that. Is that true, Edis? Show me a... Yep, everyone can see it. Good. Okay, so you can see CUAVA-1 there sitting on a stand. It's actually in the thermal vacuum chamber called Wombat XL at the Advanced Instrumentation Technology Center at the ANU at Mount Stromlo. The wires that you can see coming out of the top, which sometimes you might call braids of hair, are the antennas for radio communication to the ground and also to receive signals back from the ground. The black panels on the side there are of the spacecraft or solar cells. And you can see the main white panel in the middle there with two eyes, you might say. Those are the apertures for the EST instrument that contains the camera, spectrograph, and then the tiny TOL instrument. And right in the center there, you can see the antenna It's just a little square block, which is the antenna for the GPS receiver that June is in charge of. Let me just see whether there's any other questions. Okay, so any questions for the moment about CUAVA-1? I believe maybe I'll stop sharing that for the moment to see whether there's anything different on the live feed. There's a question here from Naif Al-Salem about whether we want to talk about plans for CUAVA-2 and CUAVA-3, intended payloads and objectives. We could certainly do that. I one level hesitate to do so because our focus here should be about CUAVA-1. So maybe we should talk about CUAVA-1 now, and then later on perhaps we'll talk about CUAVA-2/3 and the Waratah Seed project. And I agree, Marianne, we do not want to miss the launch itself. But we do have the feed, I think, the official NASA feed. We've still got 6 minutes and 47 seconds to go. So what are the experiments on CUAVA-1? A quick summary is that we have 4 payloads and 2 technical demonstrations. The technical demonstrations are solar cells from our partner Aerowave Communications and a power over data network that's integrated into the radiation counter. Radiation counter, you might say, is a space weather experiment, looking at energetic particles which have come from the sun, generally being brought into the Earth's magnetosphere and are bouncing back and forth. And those vary substantially as a function of time and can significantly affect spacecraft electronics, as well as irradiate humans, etc. And Edis Seaton's experiment called RUSH on CUAVA-1 is going to be looking at the effects of the radiation on the spacecraft on his experiment's electronics. We also have 2 other experiments, a GPS receiver and instrument, which is from UNSW with June Wen-chung and Andrew Dempster. And then we have the EST instrument, which is a 3-in-1 imaging assembly with a rather good camera, a spectrograph, and then the tiny TOL instrument, with the first 2 looking at the Earth and the last one, tiny TOL, a pathfinder towards looking for exoplanets around nearby binary star systems. So that's, I guess, what we would like to say about CUAVA-1 at the moment. Okay, so a question here from Peter Axtons. I might take this one if you don't mind. Has the fleet of instruments/payloads as originally envisioned been delivered? And the question, of course, or the answer to that, of course, it depends what you mean by originally envisioned. So we did have one of our instruments not be able to be delivered, and so we substituted the RUSH experiment instead, which we're very lucky to be able to have. Edis Seaton and his people worked extremely hard at short notice to get RUSH ready. But the other 3 instruments, the radiation counter, the ISTI, and the GPS are essentially as envisaged. Okay, so I think, so we've got 3 minutes. I think what we might do is listen to the live feed from NASA now, and then we'll be available to answer questions in a little while. And I noticed that we have, before we go there, just notice the people we do have on our panel. We've got Shulian Bai, who's the training center engineer, Jason Held, who's the CEO of Sabre Astronautics, and who's going to, we're really happy to be involved with as a partner in CUAVA, and also will be working with the the Spacecraft Operations Center down in Adelaide to connect CUAVA to Australia and the world. We're really looking forward to that. Etta Sitton from Macquarie University, Jun Wen-chung from UNSW, and of course myself, Eva Cairns, and Shirley Ann Bai are from University of Sydney. So let's hear what the official live stream is saying, and we'll come back to the questions in a little bit.
Dragon is undergoing vehicle health checks, and we did hear the call out T-minus 5 minutes for internal power. Switch to internal power, meaning it's living on its own, apart from ground support systems, which is great. We're also expecting right now the checkouts of the second stage thrust vector control actuators are underway. This is what we affectionately refer to as the engine wiggle test. Not very technical, but definitely kind of describes what we're talking about. We're moving the nozzles of those engines on the engine on the second stage to ensure we have control for the uphill climbing and navigating that vehicle. That's just part of making sure
I think at the moment we're trying to fix the issue with multiple audio streams. But if I step into the breach here at 1 minute and 30 seconds.
About 2 degrees away from Falcon 9 in order to prepare for liftoff. That strongback is part of the transporter erector. You can see on screen right now, it's starting to recline away from Falcon 9. The transporter erector is that large truss structure next to Falcon 9. Its job is, again, to retract away from the rocket and prepare for liftoff. At this point, RP1 fuel is completely loaded on the second stage and nearly completely loaded on the first stage. Liquid oxygen loading is currently underway on both stages and will complete around the T-minus 2 minute mark. In these last few minutes, Falcon 9 is performing final health checks on its primary communications, avionics, and propulsion systems in preparation for flight.
Dragon is undergoing vehicle health checks, and we did hear the call out T-minus 5 minutes for internal power. Switch to internal power, meaning it's living on its own, apart from ground support systems, which is great. We're also expecting right now the checkouts of the second stage thrust vector control actuators are underway. This is what we affectionately refer to as the engine wiggle test. Not very technical, but definitely kind of describes what we're talking about. We're moving the nozzles of those engines on the engine on the second stage to ensure we have control for the uphill climbing and navigating that vehicle. That's just part of making sure the guidance hardware is go for flight.
Oh, come on!
The exact same thing for all of the first stage engines, just a few seconds before ignition. All of this in preparation for our rendezvous with Space Station tomorrow morning. And Space Station right now we're on approach for. We're catching up to.
Launch load complete.
Is just over the south edge of Australia as we speak.
Dragon is in auto idle.
And we just heard the call out that LOX load has been completed. That will wrap up propellant loading for the vehicle. You can start to see some white clouds forming around Falcon 9 and Dragon. That is normal and expected for us at this stage in the countdown. That is super chill liquid oxygen starting to condense as it reaches the warmer ambient air temperatures of Florida.
Through the rest of the countdown, we're going to hear a few call outs, but by and large, we'll just listen in here and walk through as Dragon finalizes its preparations and the team verifies we're go for launch.
Falcon 9's in startup. Dragon is in countdown.
Both stages are now pressurizing for launch. Range and weather should both be good to go.
Falcon 9, CRS-23, go for launch.
That was the voice of the launch director verifying we are go.
T-minus 30 seconds. T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
Cargo Dragon takes flight. continuing a busy year of deliveries to a crew of 7 aboard the International Space Station.
Okay, go for it.
Stage 1 chamber pressure is nominal.
It's already going 300 kilometers an hour, and it's only 1 kilometer up. Really impressive.
We are 50 seconds into flight. Falcon 9 has cleared the tower and is currently headed to space. In about 15 seconds here, we're coming up on max Q. This is where the vehicle will experience the highest amount of aerodynamic pressures. And there was the call out for max Q. We actually throttled down the Merlin engines in preparation for that event. Coming up are 5 more events in rapid succession. Main engine cutoff, stage separation, first stage flip, second engine start 1, and then the boost back burn on the first stage will begin. Main engine cutoff, also known as MECO, is where all 9 M1D engines on the Falcon 9 first stage will shut down. This is followed by stage separation, or the separation of the first and second stages. From there, the first stage will flip to prepare for re-entry and landing a few minutes later. And the Merlin vacuum engine on the second stage will ignite to boost Dragon to low Earth orbit, and that's also known as SES-1. The first stage will then begin its boost back burn. That is the first of 3 burns needed to land on our drone ship today.
You can notice here the separate
main engine cutoff is coming up in about 10
Merlin
seconds.
engines.
Main engine cutoff.
Stage separation confirmed.
We're going to orbit, people. We're going.
Impact ignition.
So look at that, we're already almost 90 kilometers altitude.
Okay, those were those 5 events. A lot happening on screen. Main engine cutoff, stage separation. The first stage performed a flip. Second stage on the right-hand side of your screen ignited its Merlin vacuum engine. And on the left-hand side of the screen, we're in the middle of that first stage boost back burn. Looks like we are getting some really cool views
Stage 1
of
boost back
the
shutdown.
contrails being produced by the first stage. And that was the call out for the successful completion of our first of 3 burns on the first stage. So if you're just joining us, you're watching a live webcast of the 23rd commercial resupply mission to the International Space Station for NASA. This is SpaceX's 21st mission this year, and this is the cargo configuration of our Dragon spacecraft.
Acquisition of signal at Bermuda.
You might be interested to know, in order to get into space, the rocket has to do more than just go up. It actually has to go sideways really, really fast. At liftoff, gravity is pulling straight down the rocket, and as we ascend, we tilt the engines. That turns the rockets horizontally. Now, we're still going up, but we're also heading horizontally away from the launch pad in what we call a gravity turn. The rocket typically needs to go about 7.5 kilometers per second, or 17,500 miles per hour horizontally, in order to avoid being pulled back down to Earth and get into orbit. On screen again is the view of the Merlin vacuum engine on the second stage. On the opposite end of that engine is our Dragon. Next event for today's mission is the re-entry burn for the first stage. That's the second of 3 burns. This is where 3 of the Merlin engines will reignite, and this helps to slow down the stage as it re-enters the upper parts of the Earth's atmosphere. And that the beginning of that burn is happening in just under a minute. Seems like we've lost the video footage of the first stage. Hopefully we can get it back.
One of the impressive things, everyone, of course, is the SpaceX
on the bottom left-hand side,
going back down to the ground safely and landing on a
speedometer of
drone.
sorts, tracking the velocity of the first stage. As we begin that second burn, watch for that speed to slow down, and definitely once we hit the denser parts of the atmosphere, we'll start to see the speed slow down quite significantly.
So Anita asks what the engine burns.
Stage 1, entry burn startup.
Stage 2, etc. At the moment, I don't remember the answer.
And there is the beginning of the entry burn.
Anyone on the team remember?
Have relit and are currently slowing down the first
Stage
stage.
1, entry burn shutdown.
Awesome. That is the successful completion of the second burn. We are about 60 seconds away from landing, and the vehicle is traveling about 900 miles an hour. This really puts into perspective the deceleration. In the span of less than a minute, we'll have reduced the speed from the speed of a jet all the way down to 0 as the rocket lands.
So at the moment, CUAVA-1's at 193 kilometers.
This is our brand new drone ship, a short-fall Gravitas.
So we really are in space now.
First time that we are
SpaceX
making
is
a
great.
landing attempt.
Their reliability is just amazing.
Perched out in the Atlantic Ocean, waiting for that first stage booster to return to it.
Thank you, Chancellor.
Stage 1, landing burn startup.
Boost coming down to the landing stage for the booster rockets on the left.
Engine number 9 has
Always
relit
impressive to see.
in preparation for landing.
Here you can see the actual footage from the barge.
Stage 1, landing leg deploy. Stage 1, landing confirmed.
Okay.
And that is the 90th successful landing for an orbital class rocket, and the very first for our new drone ship, a shortfall of Gravitas. That is a beautiful thing to see, and a great way to start off today's mission. Next event coming up is for the second stage. The Merlin vacuum engine will shut off its engine in an event called second engine cutoff, also known as SECO. And shortly after SECO, we'll be entering a coast phase and waiting for that confirmation of a good orbit.
So we are definitely going up to the International Space Station, about halfway up in terms of altitude. Got another 200 kilometers to go, approximately. But most of that we will not stay to watch.
Nominal orbit insertion.
And we did get confirmation of both SECO, second engine cutoff, and a nominal orbital insertion. Now, the second stage has one last major task, and that is commanding separation of Dragon a couple of minutes from now. Again, this is the second flight for this particular Dragon and the first reuse of our upgraded cargo vehicle. We should have video of Dragon separation from the top of the second stage. It'll give us a nice view into Dragon's unpressurized cargo trunk. And when this Dragon makes its way to the International Space Station, it will be joining the Crew 2 vehicle Endeavour, currently on orbit and attached to the International Space Station. It's going to be super cool to see two Dragons docked to the International Space Station once again. And again, for cargo, we will be delivering over 4,800 pounds of science, research, crew supplies, and vehicle hardware to the orbiting laboratory and its crew. This includes the brine shrimps and ants that we had talked about earlier in the broadcast.
And for most of us here, the
research
important
being
thing
done
for
in
us is
microgravity on the
CUAVA-1.
International Space Station has benefited our lives here on Earth for decades. What's really cool is that our new Cargo Dragon vehicle is also able to act as a laboratory in the advancement of this science and research. We call this capability Extend the Lab. It allows some powered payloads to remain on Dragon for experimentation during the duration of the mission. This is especially helpful when there is limited to no space on station for additional science, and it also helps cut down the amount of time to...
Okay, great. So we are in orbit now. We will get to the space. So well done, everyone. Absolutely fantastic. We are going to space again, and this is going to be an exciting time for all of us at CUAVA, and hopefully for all of our partners in the training center and our host, the University of Sydney, of course, UNSW, Macquarie, our 4 industry partners, including Sabre Astronautics, and our 3 government labs. Really exciting for all of us, and we're looking forward to, well, to telling you all about it in the months to come. But first, I guess we have a few questions coming in. There's one from my better half, which is how long it takes. It would take the Dragon capsule to get up to the ISS. I think Chris Betters is answering this, but it's of order somewhere, I think, between 8 hours and a day. So the next question is from Marianne Large. When will we get to see the launch from the ISS later? And the answer is yes to that. That should be possible. We're expecting to reach the ISS on the 30th, at least US time. So it is roughly 24 hours. We're expecting to be on the space station for approximately 6 weeks, and in the first week of October, we expect Space BD and JAXA, the Japanese Space Agency, to deploy CUAVA-1 from the, I'll call it a deployer tube, which is attached to the outside of the space station. And we then expect that to be deployed, so in early October. Now, do we have any other questions? So I can't see the chat at the moment. I can see the other. Okay. So do we have any other questions or comments, things that people would like us to answer? I think you... No? Okay, so panel members, is there anything you'd like to say to our audience, our quiet audience at the moment? Any particular things of particular importance you'd like to point out about your payloads, or about the mission operations, for instance, or the engineering? No? Well, there is a question here from Anita Ho-Bailey about how long we expect CUAVA-1 to stay in space. And the answer for that in detail is we don't know. It partly depends upon, well, how many big space weather events occur, which if you have enough solar flare X-rays, for instance, you can ionize and heat quite a lot, well, more of the atmosphere, and the atmosphere puffs up and gives you more drag, which will then more rapidly bring us back in and back to the Earth and burn up. So we don't know for sure, but we'll look. And another thing that can happen is if we're not able to, what's the right term, stabilize the spin or tumbling of the spacecraft, then we will have more drag. But we're expecting to live in space for about 1 year to 18 months. That's the sort of timeline that we're looking at. Okay, so question, here am I answering all these questions. Okay, so Shirley-Ann, here's a question for you from Marianne. When will we expect to start getting data?
Hopefully immediately after it's deployed. But that would depend on when exactly it will be deployed and when will be the first access to the Sydney ground station. But we hope to get the signal within the 24 hours, or hopefully within first weeks, we can conclude the health status of the CUAVA-1 satellite and what is happening on board of the satellite.
Yep.
Yeah.
So at least some of the data will be contained in the beacon. At least once the radiation counter turns on, we'll get radiation counter data in the beacon. And that hopefully will be relatively quick. But as Shirley-Ann said, there is a commissioning phase after the spacecraft turns on before we will really start getting significant data. So we're looking at hopefully mid-October, might be late October before we really start getting data.
If I could help answer some of the operational questions.
Go ahead.
Rather than forcing all this on you guys. So what's going to happen is the satellite is on its way to the International Space Station. When it's there, it's going to be there for about a month, maybe a little longer, usually because the astronauts that do the deployment, they've got a lot of work to do themselves, and they have a schedule and a very finely defined schedule for them. And we've been slotted inside that schedule. So when we get the green light to be deployed through the Space BD, then the deployment happens from the International Space Station. The satellite, as we said yesterday, is going to be in cold storage for a fair amount of time. So it's if we're lucky, we'll get a response right away. What is normal to happen is it normally takes a couple of weeks to get a first response. And we'll sometimes get deployed, not just ourselves, but with a bunch of other satellites that are deployed in the same cohort, if you will. So that's going to be the operational task, is trying to connect with the satellite first and foremost. If that satellite, once it turns on, it might turn on in a low power state. So sometimes it takes a bit of time and a couple of orbits to actually charge up the batteries and trickle charge in. So eventually we'll be able to talk to it, for sure. So it usually takes up to a couple of weeks. So if some people say, hey, let's have a big party when it deploys. Yes, let's do that. But actually, let's do that, but also realize that you might not get a signal back right away. And it doesn't mean one thing or another. It's just waiting for the satellite to get enough juice to come back on enough to get a signal back down to Earth. That's usually what happens.
That's excellent. Thank you, Jason. And so there are, so I think Alex's question about why the satellite launch will be in 6 weeks was just answered by Jason. It really depends on the scheduling of astronaut tasks on the space station. And Space VD has told us it's likely that first week in October. So team, do we expect there to be a team party to celebrate? Yes. In fact, this is an opportune time to say, did anyone bring their drinks with them? Now, of course, it could be something virtuous, like a flask here, which might or might not contain water. And is everyone ready for a toast?
Yeah.
Okay, let's get our drinks. Please, everybody, join us. I at least am going to have a CUAVA cocktail. Which has guava juice, pineapple juice, actually banana, rum, ice, and lemon and lime. So I guess I would like us all to have a toast, virtually or not, to CUAVA-1 and a very successful mission. So CUAVA-1 and success.
Cheers.
Cheers. Congratulations, team.
Ding, ding.
Congratulations to everybody. As you all know, this has been a major effort for many of us, well over 50 of us. And so it's a great thrill to actually get into orbit now. I mean, just amazing. 20 minutes ago, we were down on the ground. Now we're in orbit. Quite amazing to think of. Quite amazing. And Okay, so yes, Steve, Marshall, there will be a good party. We've had a very small impromptu one here. Once we get out of lockdown, we can, and especially once we get some data, we can expect some excellent parties. I suspect there'll be one with Sabre and the mission control people once we get the first signals from an Australian satellite down there.
That's when the real party is going to begin.
Yeah.
That first signal, you get that first signal. That's when you start knocking back the whiskeys. Maybe one whiskey. Now the operators aren't drinking whiskeys.
Just virtually. Excellent, excellent. So I have a question here. And so Marianne, the answer to your question about the launch from the ISS, who would like to take that? June, you know the answer to this.
Sorry, can I get the question again?
The question's, will we get to see the launch from the ISS later?
I think yeah. I think we did that last time. I think we haven't got the link yet, but we'll probably get a link very soon, specifically for that purpose. Yeah.
Yeah, absolutely. We'll get that one.
Yeah.
We did for Inspire 2 and UNSW Eco, and Space BD definitely wants to have a deployment party, and they want to have it at high level, actually, with a Japanese minister on the line as well. So well, that would be.
We hope to choose it to be on the daylight side instead of on the eclipse side, so we can see it actually.
That's right. That's right. I mean, there are many good reasons for that. Yes, excellent. Okay, so a question from Anna Pavlicic. Sorry, Anna. Which parts of CUAVA-1 will be used again for CUAVA-2 and 3, and which do you intend to re-engineer or replace? Will it depend on the performance of CUAVA-1? So maybe, Julianne, do you want to say something here?
Yeah, sure. So the avionics stack, the OBC, the onboard controller, the radio, the ADCS system, at least a part of the ADCS system will remain the same. We intend to keep as much as possible for the existing hardware, so we don't have to do the software again. But we do want to add a high-speed comm radio, whether it's S-band or X-band for the next mission, because the data downlink amount will be much larger. So there will be a better ADCS with 3 reaction wheels, so we can do more accurate pointing for the science missions. Yeah, I think that's pretty much it. All right, back to you.
So maybe it's an appropriate time for perhaps Chris and June to say something about the instruments that they're hoping to develop for CUAVA-2/3. So maybe Chris, do you want to say something here? And then we'll go to June, and then we'll maybe.
Yeah, I mean, so we're hoping to build on what's in the current one to convert it into like a proper full hyperspectral imager. The kind of science goals behind it are looking at blue carbon, which is a lot of carbon sinks are actually along coastal fringes, and getting more information on them, particularly timely data where you can have observations multiple times a month, will help the scientists understand what's happening there a bit better. So that's kind of the brief of the instrument that we're working on right now.
Excellent. And June, what would you like to say about the GPS receiver, or instrument rather, for CUAVA-2/3?
Yeah, so CUAVA-1 is really just a pathfinder. It's a tech demonstrator for our custom GPS receiver, which will scale up to 2 of them in CUAVA-2, but those 2 will be used for a reflectometry experiment, which is our primary experiment. There's obviously a lot of spin-off from that, but yeah, it will be very interesting to see those data. We'll be the first one in Australia to do a GPS reflectometry if we do manage to achieve that goal in CUAVA-2.
And reflectometry involves not just detecting the direct signals from the GPS satellites, but also the signals that are reflected off the sea, for instance, or the ocean, right?
Yes. So one of the primary products will be sea surface roughness, sea winds. So data products like that can be derived from the observed delayed Doppler map, which is the data product that we can get out of the satellite. And that would be very exciting for us if we can do that.
Edis, is there anything you'd like to say about possible instruments?
Yes, I think for us, we have the payload, so it's going to be mainly the firmware that gets updated. So we are able to send our latest designs up there and see how they compare to one another. So I think in this area, and also have a look at combining it with other instruments and having data flown into Rush, and then we can do onboard processing and provide results and then feed that back. I think we'll be exploring those opportunities for future CUAVA missions with the partners.
So the FPGAs that you have on board could potentially be used to process data from Chris's instrument, for instance.
Indeed. So one of our aims is to do the onboard processing in a reliable way and recover from the radiation-induced errors in space. So it can. So that would be a great exemplar for us to use to get the data and then process it.
Right. And then, yes, the other instrument, maybe I should comment on the other instruments and technology we're expecting to have on CUAVA-2/3. We're expecting to have a plasma wave instrument, which will be able to detect the thermal waves in the plasma and be able to get the electron number density and temperature in the ionosphere as a function of time, a function of position, function of space weather events. And that will be very, very interesting for a lot of people. The ionosphere is relatively poorly known from the point of view of the variability of the electron density. We also expect to have a plasma thruster, which will allow us to change the velocity of our satellite. Might not be quite as full of thrust as we might have hoped. It might be down at the micronewton level rather than at the millinewton level that some people would like, but it should be very interesting. And I think I'm forgetting one, aren't I, Shirley-Ann? Oh yes, I'm forgetting the Sabre Astronautics Drag-N, which is a deorbiting device. It's a tether, as in a long conducting wire that gets dragged out behind the spacecraft, induces a current on it, and then there's a force acting on the wire and the spacecraft that will deorbit the spacecraft. Is there anything else, Shirley-Ann, that I'm forgetting at the moment?
The cross one, the Star Tracker.
Yes.
Have you mentioned the Star Tracker?
Yes.
So we have team. Yeah, so we have a student team build a in-house designed wide field of view Star Tracker, and we intend to fly that to cross compare with another Star Tracker that we bought from CubeADCS and see if that is good and can be used for the future missions.
Okay. Excellent. June, would you like to answer this Peter Axton's question about the GPS?
Yeah, that's an interesting one. So there is nothing stopping us from doing that in theory, but in practice, we have programmed it to keep track of only GPS L1 signals for now. So that's the conventional American GPS signals that are currently in service. So we can do that if there is special help from the and special interest from certain people, but currently we haven't programmed it to do so, and it can be reprogrammed in space for the next iteration of this, which is in CUAVA-2. So happy to discuss more about that.
Excellent, June. Right, and Jason is answering a question for Julian Michello about single event upsets.
I could just talk through that, I guess. Yes. So that I actually really love this one because of Edis's instrument, which actually wants some sort of radiation or some damage to be able to see how it responds to it. So that's actually, this is the first CubeSat I've ever seen where any damage to the CubeSat is actually really, really good data to have in its science. But the Responsive Space Operations Center in Adelaide is going to be getting space weather data at the fastest tick rate from Bureau of Meteorology here in Sydney, as well as National Oceanic and Atmospheric Administration in the United States. and we're going to be getting the best possible estimate of what could happen. At the end of the day, CubeSats are very small and they're not radiation protected. So we're going to expect a lot of activity on that spacecraft over the next couple of months. And rather than saying, okay, it could damage the spacecraft, it's actually exciting to take the opposite approach. Is well, let's see how it actually breaks and see what we can learn from that.
So it's particularly exciting then actually in the current CUAVA-1 that we have both a radiation detector, which should, which will be detecting radiation events, energetic particles hitting the spacecraft. And at the same time, we've got the single event upset instrument, RUSH, which should be seeing occasionally at least upsets associated with those radiation events. And then EDIS's FPGAs will be doing various using various algorithms to try and repair the damage caused. So it will be a very interesting combination to have there. Okay. So everyone, I think this is a time for us to celebrate and to rest for a little while for a job well done. Well done, team. It's been fantastic. Of course, even though this is perhaps the most visible step, the one with the most, in some sense, catastrophic or at least explosion-like type of problems that could occur for it, it's only one step on our road. Because as you've heard, we have to be deployed from the ISS. We then have to come alive in space with sufficient charge to be able to start our onboard computer and deploy the antennas and bring the spacecraft up. We then have to commission the instruments and get our data and keep running this carefully and well for a good while. You know, we're looking at 12 to 18 months. So we have a very exciting journey ahead of us for this spacecraft, and we will. So we can celebrate a bit now. We have gotten into orbit with it, and we've got to, so to speak, experience space ourselves directly for the spacecraft. That hasn't yet happened. It will, but we are a major step along our road. And this is CUAVA's first CubeSat. We've been working on it for about 3 years, and now we're going to accelerate. We expect to have 2 more CubeSats in the next year and a bit. One is the CUAVA-2/3 CubeSat you've just heard about, and the other is called Waratah Seed, which is a rideshare satellite carrying payloads for industry groups primarily, but also other groups who will pay us suitable amounts of money to carry them. So it's a very interesting time for Australia's space industry from our point of view, and the space sector generally. We are, of course, only a small part of the ecosystem for space in Australia, but we look forward to making major contributions to that, to the Australian space sector and globally. So thank you all very much, team, for being here, and panel in particular. Most of the panel members are the instrument leads for CUAVA-1 instruments. And thank you very much, audience, as well. We hope you've really enjoyed it, and we hope you will follow our journey further with us as we venture into space. So thank you all very much for coming, and we look forward to being in contact in the future with some more exciting news, most likely about 6 weeks from now when we get deployed into space. So thank you very much, and good night.
Thank you, Eva.
Right. Thank you all.